Hi everybody, welcome back. Welcome to the next video in our astronomy series, this time with Unit 3 on light and matter. So today we're going to give a very brief discussion of the types of matter out there, particularly some of the matter that's out there in space, and how this can potentially be relevant to astronomy. So first of all, what is matter? Well, it's hard to get a formal definition of matter, but for our purposes, we'll think of it as anything that has positive energy that it can transfer to other matter, and back and forth. In other words, this kind of distinguishes it from radiation, because radiation is an essence of the energy itself. So it's not allowed to travel at the speed of light, though don't ask me how neutrinos fall into this category. And a corollary of this definition is that matter is not part of space itself. It's something that exists within space and can travel through it. Now, in terms of a substance, we used to think of matter as just either a solid, liquid, or gas back when we were in elementary and middle school, and then when we were in high school we were told that there was this fourth phase of matter called plasma, but we now recognize that there are lots of other phases of matter as well, things like Bose-Einstein condensates, fermionic condensates, strange matter, quark-gluon plasmas, various degenerate types of matter, etc., and then whatever the heck dark matter is. And some of this is important for when we will discuss white dwarfs and neutron stars, as well as the Big Bang, because particularly these degenerate states of matter are extremely important with white dwarf stars, and they're also important in the cores of the giant planets. So, solids. We're familiar with solids. They tend to either have some sort of amorphous or crystalline structure that falls into place into either a nested fashion or just some random blob that stays there. And its temperature is indicated by how rapidly the molecules are able to vibrate within that structure. And as a result of this, very cold ice is a lot more difficult to break than ice of the same thickness that's near what we think of as the melting point of water, or the melting point of ice, the freezing point of water. And in fact, the ice on a lot of the moons in the outer solar system is like as hard as granite. Now, liquids are situations where the molecules are able to break free of their bonds in that crystal lattice or powdered structure, and they're able to flow around. And like you move the container a little bit, and they'll flow around until the top of it has a horizontal surface. And there are still some intermolecular interactions that cause these to kind of stick together, but they tend to just kind of fall with gravity. They exhibit pressure, and so the top ends up having that horizontal surface. Warmer liquids are usually less viscous, meaning that they behave more like water and less like maple syrup. And that's because the kinetic energy of the atoms or molecules tends to be higher, and thus the intermolecular interactions play a smaller role. Now, gases are situations where the atoms or molecules of what would otherwise be a solid or a liquid have kind of broken free completely of their interactions, at least their interactions with large bulk numbers of their members. And they have enough kinetic energy basically to fly around the container in projectile motion. So remaining interactions are going to be with other gas molecules, and they will just be collisions, but they're not really going to stick together during these collisions most of the time, unless they happen to be molecules of different gases that naturally like to bond together and haven't yet done so. So they're free to fly around. Plasmas are a completely different state. People often just think of, oh, a plasma is just a really hot gas. Well, it's more than a really hot gas. A plasma is a situation where something that had been a gas is dealing with molecules that are colliding with enough kinetic energy that they're able to knock electrons loose. And since the electrons have been knocked loose, these are no longer atoms, they are ions. And plasmas, as a result of being ions, they are charged, and since they're charged, they behave very differently when they're interacting with a lot of other phases of matter, and also when they're interacting with electric and magnetic fields. So these plasmas really are a completely separate phase of matter. And in addition to that, other than dark matter, again, whatever the heck that is, plasma is by far the most common phase of matter in the universe. So that's something important to keep in mind. Plasmas are the most common phase of ordinary matter in the universe. Now again, we have other phases of matter, but plasmas are going to be what we're going to be dealing with a lot in this course later on. And we're not really going to worry about things like quark-gluon plasmas, except maybe when we talk about the state of the universe just after the Big Bang. But we will talk about degenerate phases of matter when we get to discussing the cores of Jupiter and Saturn, as well as white dwarf stars. So we'll come back to some of these later. Now the reality is that even when you consider matter in a particular phase, not all of the atoms have that phase. So for example, if you have a cup of water and you just leave it out in the open, eventually it's going to evaporate. The reason it's going to evaporate is because some of those water molecules have enough kinetic energy that they're allowed to kind of break free. They act as projectiles. In other words, not all molecules in a substance have the same temperature. Instead, there is a temperature distribution, something called a Maxwell-Boltzmann velocity distribution. Now, why does water evaporate? Let's give a picture of this. Here we have a graph, which I actually stole this from a chemistry diagram, talking about activation energy, the necessary energy to really get particles to react with each other and form compounds. But you can think of this very similarly as the boiling point of a substance. And you have this Maxwell-Boltzmann velocity distribution, and the idea is that some of the molecules have enough kinetic energy that they actually are above what you would normally think of as the boiling point, where this mark would be kind of the average kinetic energy of something that would be boiling. Well, here, the vast majority of the molecules are far below that, but some of them are above that. Well, the ones that are above that, well, guess what? They become projectiles, and as projectiles, what do? They leave. And since they leave, they don't come back unless a few just happen to by random chance. So that's why you end up getting evaporation in an open container. If you close the container, then sure, some of these molecules will end up being higher than the boiling point, but when they do so, they're just going to bounce off the edges of the container and recombine with the liquid. Although that bouncing off and interaction, some of them will combine together and end up binding kind of above there and becoming liquid at the top of the container. That's why when you put a cover over a glass of water, that cover will often have little water droplets at the top. Now, if you have your container being open, the ones that leave, well, the ones that leave are the ones that have the highest kinetic energy. As a result, the average kinetic energy goes down. Well, that's called evaporative cooling. And you can speed this process up by blowing air over your liquid. And you end up having the evaporative cooling occurring much faster because the molecules that are just kind of barely around the threshold to evaporate off and leave, well, they're given some extra energy, and by that blowing, they're taken away. And the ones that are kind of near that threshold, some of them will kind of recombine and come back to the container. Well, by blowing over it, you prevent that from happening. That's why blowing on a cup of hot tea or hot chocolate ends up cooling it down more quickly. Now, how does matter interact with light? Usually we think of solids and liquids as being relatively opaque to light of various wavelengths. Sure, there are certain wavelength bands where light is able to pass through solids and liquids, depending on what kind of solid or liquid you're dealing with. I mean, we're familiar with glass, quartz, etc. And even gases can sometimes be opaque, or at least translucent, because think chlorine gas. Dense chlorine gas is a bit greenish. And denser gases are going to be completely opaque to light of certain wavelengths, as we have already discussed when talking about the fact that with the greenhouse effect, many infrared wavelengths are absorbed by the water vapor and to some extent the CO2 in Earth's atmosphere. In other words, our atmosphere is opaque to those wavelengths. Our atmosphere is thankfully opaque to gamma rays and X-rays. So, light that's being absorbed by a solid can heat the material, causing the molecules to move faster. and we'll have more to say about this later when we talk about blackbody radiation in the next video. And the same is true of light that's being absorbed by a dense gas. Now we can learn a lot about light interacting with gases and about the gases themselves because of this interaction. Because, after all, gases and plasmas make up so much of the interstellar medium, which is the areas between the stars. And analyzing light that's interacting with those molecules can yield a lot of information, not only about the source that originally emitted the light, but also about the material that is between us and the light source. So we're going to discuss that in a bit more detail in the next video. So thank you for watching, and I'll see you then.